Thank you. All right, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day we have just to meet together and to talk about your creation. We thank you for math, and I just pray that you'd help us to enjoy it today, Lord. In your name I pray. Amen. All right, so I had this idea, I think, that I should talk about like the jet space and the differential equations and things first in order to motivate Frobenius Theorem, but I think it's the other way around. So I'm going to talk more about Frobenius Theorem again today, and if I behave properly, we should at least talk a little bit about differential equations at the end. So there are a few competing notions here, basically. So we're going to talk about vectors, forms, foliations. All right. So in particular, the backdrop here is going to be a smooth manifold. So we're going to let M be smooth, n-dimensional manifold. Okay, that's going to be the case throughout the lecture. I don't want to say that 30 times, so let's just fix that. And we're going to let D be a k-dimensional distribution. So what this means is that D is a subset of the tangent bundle of M. What's the tangent bundle of M? Right, we just basically take all the tangent spaces at all the points in M, we just glue them together, give them the natural manifold structure. That's the tangent bundle. So D is a subset. So what this in particular means is that there is a smooth, whatever that means, assignment. I'm not going to make that rigorous in here, okay? D sub P, an element of TP, not an element, but subspace of TPM for each P and M. So a k-dimensional distribution is the selection, like the smooth selection of a k-dimensional subspace of each tangent space. All right. Now, something that I should talk about, because I'll be using this language today, at least a fair amount, is the notion of a section. A section, let's say X, an element of the section of M, Tm, let's say. What this basically means is that X assigns a vector to each P in M. In particular, P maps to X sub P, which is an element of TPM. There are better, more function theoretic ways of stating this, but I don't want to distract. All right. But so this is a section then. What is a section of the tangent bundle? In plain language, it's a it's a vector field. We're giving we're attaching a tangent vector to each point, right? So you could also talk about, section. You could talk about a section over U, right? Then that would, of Tm. Then that would be basically, that's another way of saying vector field on U, all right? So, or you could talk about a section over U of T star M, the cotangent bundle. This would be if the section was, omega, that would mean that omega is smooth one form on U. Okay? And you can also talk about sections of the distribution. That would basically be a local, like a, if I have a section of the distribution over some subset, say U, that would be like a vector field whose vectors lie in the distribution D, all right? So, definition, if D is, again, a distribution, smooth distribution, then N, a submanifold of M, technically an immersed submanifold, but I haven't really gone into those kinds of details. There's different kinds of submanifolds when you study these things more carefully. But anyway, it's an immersed submanifold such that the tangent space to P at N is equal to D sub P for each P in the submanifold N. Then we say is called then, let's say bad grammar, but makes N an integral submanifold, or just an integral manifold of the distribution. All right, so this kind of, so typically when we talk about distributions, the way we communicate their structure for specific examples, what we do is we give a specific like set of vector fields which generate them. So some examples. Here's an easy one. We can let D basically be generated by partial x, comma partial y, right? I mean this set of vector fields, all right, on R3. I talked about this a little bit last time. The integral manifolds of this are what? So I want some like subset of R3 whose tangent vectors fall in the span of partial x and partial y at each point on M. So like, it's basically N here would be something like x, y, z such that what? Yeah, z is fixed. X and y free to range over R2, right? You can easily see then that the tangent space to P of N is nothing more than the span, right, of partial x at P, partial y at P. Another example, actually two examples. In Rn, you can look at x equal to like x1 partial x1 plus x2 partial x2 plus plus xn partial xn. So what is this? In our usual bracket notation, this would be like, in R3, it would be the vector x comma y comma z. This is exactly the radial vector from the origin. And actually not for for Rn. So we're talking about the version of Frobenius theorem, and this whole discussion we're talking about in here is the more naive one. In principle, you could look at this theory where the leaves in the foliations are not, oh, I don't know what that is, but the integral submanifolds are not of equal dimension. You could have not a regular distribution. The distribution I've talked about here is regular because the rank of the distribution, the dimension of the subspace which it selects, is constant throughout the manifold. If I was to work with this on Rn, this, if I just look at the distribution spanned by X, this has rank 1 most places, except for the origin, right? So, anyway, so what we do is throw out the origin for the sake of adhering to the general theoretical discussion today, and let that be M, right? So then the this suggests the if this if D is equal to, let's say, if you'll allow me this rather sloppy notation, say D is generated by this X. Not a notation I've seen in a textbook, just a notation I'm using for today. Beware of it. Okay. Then what are the integral submanifolds? Well, N is just something like, what? So what does it mean to find an integral submanifold to a vector field? What are we actually solving? Let me just, how do you find it? Let me actually calculate it for a second here. How to find? How do you find the integral manifolds of X? A single given X. How do you do that? You need to solve the condition that the vector field be tangent, right, to its, so let me just, it's easier for me to write the equation than to put it into words. What we want is we want some curve, basically, gamma, right, let's say from the reals to M, right, such that what? X of gamma of t is equal to d gamma dt. Now, a typical abusive notation is just to write gamma is equal to x, x1, x2 dot xn. In that notation, what does this condition be? Well, this condition becomes x1 partial x1 plus x2 partial x2 plus plus xn partial xn is equal to, well, d gamma dt. What's d gamma dt? In this notation, this becomes, it becomes dx, well, let me use summation notation here. It becomes the sum I equals 1 to n of dxi dt partial xi. Remember, we use partial xi, and this has to be at the point gamma of t, technically. But I won't write that in the next step. So I'm being sloppy and not writing that down here, but that's, or you could say I'm writing it as a function equation. I don't know, whatever floats your boat. The point is we've got dx1 dt partial x1 plus plus dxn dt partial xn. So what do we have to find this curve which lines up with the vector field, this integral curve, integral manifold, one-dimensional manifold? What do we have to? We have to solve a system of differential equations. What is the system of differential equations we have to solve? We could solve these. It's just this: dxi dt is equal to x of I. Right? It's just ka-chunk. I mean, it's very boring. Can you solve the system? What's the solution? Let's say x sub naught. X sub naught I, that's particular constants, e to the t, right? So, of course, you see that this can't be what? It can't be 0. So what we have then is a ray from the origin, which geometrically, I think it's, once you understand what X is, it's totally unsurprising that I tell you that these are the integral manifolds, And you see there's something funny about the origin, right? It's where all these integral manifolds come together. Again, these integral manifolds are examples of leaves in a foliation. What is a foliation? A foliation, I don't want to write it down. I don't even want to write it down. I'm just going to say it in words. Foliation, a k-dimensional foliation, is a collection. It's a collection of submanifolds of a given manifold, each of dimension k, all right, whose union fills the whole manifold, and they're connected. Each leaf in the foliation is connected, and they're disjoint, like this. See, if you throw in the origin, they're not disjoint. They intersect at the origin. That's exactly where this distribution fails to be regular. That's not an accident. And you can prove, given certain conditions we'll talk about today, that the leaves in the foliation, in fact, are disjoint and satisfy these conditions. We'll talk about something called a flat chart, which then says that, if you take an open set in the manifold and look at its intersection with the foliation, what you get is copies of, you intersect. If you think about, imagine you had a stack of leaves, right? And you just kind of could somehow with a laser cut out a stack of them or something. Maybe that's the wrong thing. How about an onion is better, maybe a better thing to think about. If you could take an onion and use one of those apple cores and just go pull out a core of the onion, you'd have the different layers in the onion separated, right? And a particular open set of the onion would cut through they'd be disjoint, there'd be finitely many of them, and each one of them would be isomorphic or diffeomorphic, let's say, to a square. And that's more generally what has to be for these foliations, is they have to intersect such that the chart allows a diffeomorphism to a cube in Rn. But I'm probably not going to get to that level of sophistication today. It's just for your own informational purposes. Anyway, so there's the integral manifold of X. So N here could be something like basically I guess you could write it this way: T times X, Y, Z, such that T is an element of 0 to infinity. That's a reparameterization of the solution we found, right? In particular, this thing I just wrote is actually, this is a notation that's used. This you could write as gamma. This is really gamma sub T of X, Y, Z. And so what I mean by that, well, goodness gracious, I guess if I do that, I probably am supposed to do, I don't know, I'm a little bit fuzzy on some of the details here, but let me not fuss too much. But this would be the notation for the integral curve. This would be the flow of X through X, Y, Z. Now I probably need to put this to be T minus 1, like that, so that when 1 minus T rather. I don't know. I want T equals to 0 to give me this point, and I don't want it to go past the origin. What's my formula? It's T plus 1, is it? I mean, there's different, I guess if I use T plus 1, T equals to 0 gives me the point X, Y, Z, right? But then I don't want it to go past the origin, so I should let the domain be what? Yeah. Anyway, there's a whole theory of how to find flows to vector fields and how they behave and everything. You could easily spend 2-3 weeks discussing the finer points of it. All right, I'm showing you an example of a flow. And you find them by solving differential equations. They have very nice structure. But this is a nice notation. This is the flow of the vector field through that point, that much time. So this goes time t past the point x, y, z along. So like here would be the point x, y, z. And this is the flow along that vector field. So all right, so before I erase something I want to add comments to this. But one more thing. So that's this. Now, 3, which builds off this, you can talk about d perp, right? Which is just kind of what it sounds like. This is be an n minus 1 dimensional distribution formed by, vector fields which are perpendicular to x at each point. Now, it's not necessarily the case for a given distribution that you can find a vector field which covers the whole thing. Like, generally speaking, we can only find vector fields which reproduce the distribution locally. And then we'll need like different local generators at different places. You might not be able to get one system of vector fields which extends over the whole thing. So there's some nuances there. That said, my examples will all have globally defined vector fields, so they're kind of boring from a topological perspective. Because so this is a one-dimensional distribution, right? And so TPM here is n-dimensional. So basically what we have is, yes, generally, yeah. So we'd have basically, this is the structure dp, direct sum, dp perp has to be equal to TPM. Well, yeah. I guess I could try to write down the specific set of generating vector fields in Rn. I'd rather not. So let me just be kind of chicken out here a little bit and specialize. Man, when is the chicken lobby gonna get it together and stop this abuse of them? I mean, I'm always talking about chickening out. It's really poor chickens. Let's see here. R2. The way I talk about chickens. I don't know. I mean, we shouldn't really use anything. I mean, we should be sensitive. Sorry. Well, cats are indefensible, so that's a different thing. Specialized R2. So there, the x, maybe that's too simple, but x in R2, the x would be what? It would be x partial x plus y partial x, right? So really, if D is that, then D perp is generated by what? Right, because this is a vector is perpendicular to that. I mean, the dot product of vector fields is defined in the natural way. I mean, it's this times that. So this gives you xy minus yx, which is 0, right? Oh, that's supposed to be a y, yeah. Now I talked about, or I don't know if I did talk about it or not, but if you call this thing y, right? If you solve y gamma of t, right, equals to d gamma dt, that amounts to the system of equations that gives you like y partial x minus x partial y equals to, if you allow me some physics notation, x dot partial x plus y dot partial y. This gives us a system of two ordinary differential equations. In particular, we get x dot is equal to y and y dot is equal to minus x. You can solve these by substitution. This gives me x double dot is equal to y dot, but y dot is equal to minus x. Therefore, we get x double dot plus x is equal to 0, which basically says what? X is equal to, something like a times cosine of t plus some phase angle. And likewise for y. You can find y also is a sign in this case, because y is equal to x dot, right? So y is equal to minus a sine of t plus phi. So of course, we get those integral curves of y are circles, right? Okay, so I've probably said more than I need to about this part. So I guess you're then led to the question, okay, so do all distributions then have integral manifolds, right? Is there something special about the examples I've looked at here, besides the fact that they're mostly one-dimensional or codimensional one? I mean, yeah, this one was kind of interesting. Example 1. Let's look at example 4. And this is an old example. I think this example goes back to Darboux, but I can't remember where I read that or watched it. So I'm not sure. There's about 4 or 5 different things I've been looking at, and I don't know where I heard that or read it. But this is an old example, I think. And these, by the way, I'm following John Lee's Smooth Manifolds book, not to be confused with Jeffrey Lee's other book on. They're both graduate manifold theory books, right? And they're both pretty introductory and excellent. I say read both. Although Jeffrey Lee's book has some online supplement that's got like hundreds of extra pages. It's really something. Anyway, here, this is on R3. Okay. So let D be basically generated by these two guys. So let's see here. If you so think about it, if there was going to be a integral curve, well, let's see here. Suppose you tried to find an integral submanifold here, at least locally matched up at the origin, right? On the one hand, you have to include the curve that's on the, this right here, this curve has to be on there. Why is that? So this is y equals to 0. Is that an integral curve of one of these vector fields? Let me be more specific. Phi, or I've been using gamma. So gamma of t is what? Gamma of t is, I don't know, we can start it through the origin wherever you want. I mean, I'll start through origin. This would be t, 0, 0, right? That's the x-axis. Is that an integral curve? It is to x. Check it out. X of gamma of t would be what? It would be, well, partial x, actually, at t0, 0 if you want me to be picky. But on the other hand, this is also d gamma dt. By the way, it's not hard to prove that if you have an integral submanifold, right, that's built from vector fields, x and y, part of the thing that the manifold has to include are the flows, the integral curves of the vector fields which build it. So it's not unreasonable to insist that this curve, the x-axis, has to be at least locally in the proposed integral submanifold N. But can you think of any other curves which are also in this submanifold, proposed submanifold? Well, I think it's also clear that, say, beta of t equals to 0 t0 has y of beta of t equals to d beta dt, right? So, at least really close to the origin, that curve is also in there. So if I can find another curve through the origin which doesn't stay in the xy plane, we're in trouble. And I mean doesn't stay in the xy plane infinitesimally close to the origin. It'd be okay if it stayed really, really close to the xy plane and then after 1 unit of time lifted off. That wouldn't trouble me. I'm talking about infinitesimally, or like really close to the origin. Can you think of anything else here? Can you see another, something that involves z? 0, well, yeah. Oh, let's try it out. I don't know, I haven't tried. The explanation, I read a different explanation for why this isn't a submanifold, an integral manifold, and every book I read has a different explanation for why this distribution fails to. Okay, so Joe says, look at 0, 0 t. Then d alpha dt is partial z. And let's see here, x of alpha of t is what? It is partial x plus, it's just partial x. But, what? Well, if I plug in the x equals to 0, y equals to 0, so I just get partial x. I mean, the coefficient here is 1 independent of what the curve does. What's that? Yeah, I'm trying to think. Well, why don't we just try to solve it? Let's try to find a non-trivial. Let's try to solve it. So like, this would be what? This would be something like. So we have partial x, right? Plus y partial z is equal to x dot partial x plus y dot partial y plus z dot partial z, right? So we have to solve x dot equals to 1, y dot equals to y, and z dot equals to 0. We have this following solution. What did I say, alpha? Oh, y dot 0. I'm sorry. Thank you. Z dot's equal to, thank you. So this says that y is equal to y naught. This says that x is equal to t plus x naught. And this says that z is equal to y naught t plus z naught. So alpha of t equal to, say, And our x naught and y naught and z naught are all 0 for the point we're interested in. We're interested in the origin. So we just look at the curve t, 0. Oh, curses. Oh, man. That's not what I want. I already have that one. Ah, man. What if I look at the, what's up? X of beta.
Beta was 0, T 0, and we did y of beta. So if you have x of beta, you put the t in for your y term, and you get something to partially. Maybe.
Yeah, but I need another curve that is in the distribution. It's an integral curve of the distribution, but doesn't not horizontal through the origin. TT0? Oh, you can do anything you want. I mean, we can try anything. So you say like alpha of t, TT0. I mean, I'm hopeful that that will do it. I guess the point is, maybe I can't. Maybe I have to get at least a little bit off the origin. But if I get, say, just right there or something, like really close, if I get just a little bit off the origin, I start picking up. Well, maybe definitely something with y. This might. I don't know, guys. I'm sorry.
It's gotta have something in the z spot.
What's that? I'm sorry. I'll have to think about it. Let's go on. But yeah. Oh. It occurs to me I should stop being an idiot and give you a picture. So here is a little handout. It's supposed to be stapled. Where's the staple? Actually, this handout has will convince you. The essential issue is that the little plane defined by the distribution, if you look at the front page here, it shows you how the distribution actually, it's an assignment of, hand that back to Joe. So if you see how it goes. If you just go like a little bit, and even if, it doesn't matter how close you are, there's no open set around the origin which does not go to planes which are not horizontal. They tilt below the xy axis if you go back in the negative z, in the positive x. They tilt above the xy axis if you go into positive y in the positive x, and so forth. So you see that if you, and one of the things I read, it convinced me that if there would be like a helix that's an integral curve of this, but I can't see the details right now. Idiot. Anyway, so what makes this distribution different? Now that I have maybe almost convinced you that it's not possible to find an integral, and in fact, the origin is not special here. It fails to have integral curves everywhere because it has essentially that same kind of tilting. So, what is different about this distribution? It goes back to the so-called bracket of vector fields, all right? So, definition, the bracket of x and y. So this is going to be a new derivation. I'll tell you how it acts on a function. X on a function x by x of y of f minus y of x of f. So, for example, if I look at the bracket of, let's see here. Well, I'll do something simple to start with. If you have just partial x, comma, partial y, what does that do? Which is what? That's 0, right? So the bracket of my example 1, the bracket of the vector fields which built the first distribution, the bracket of them are 0, all right? In contrast, so if I look at the bracket of x and y, if you don't mind, I'm going to drop the function. So that would be like partial x plus y partial z, comma, partial y. So the bracket is bilinear. We just showed that this is 0. And this would be like y partial z partial y minus partial y of y partial z. But what is y? What is this? By the product rule, that is minus partial y partial z, minus y partial z, minus partial z. See, because when you think about how that acts on a function, you get a product of like, do I need to write it out? I can write it out. And then you drop the f, and that gets you back to this. Of course, these cancel, and you're just left with minus partial z. But if you look at this, this is not an element of the span of x and y. Where here, I really mean, you have to think about this point-wise. I mean, like partial z at the point P is not in the span of x at P and y at P, okay? It's not a span of I don't think I'm allowed to put functions there necessarily. So, definition. If D has local sections x1 dot xk such that the bracket of xi xj is once more in D, well, is once again a local section of D, then D is involutive. Doesn't have to be that the brackets are 0. That's a special thing. It could just be that the brackets are again back in. Basically, the point is if the brackets are again back in the distribution, then like the integral curves of the bracket of the two vector fields, it's again an integral curve you already had, kind of intuitively speaking. So you don't want to have the case that Because like every vector, so we're looking at these k vector fields where they're so-called a local defining, a so-called local defining frame of the distribution. So I'm assuming that they're k linearly independent vector fields, right? So each one of those vector fields comes with an integral curve, and you can kind of think about putting those together in such a way that you get a k-dimensional, because those integral curves, wherever they meet, well, excuse me, they don't meet, do they? Oh, yes, they do. I'm not saying that they're not integral curves of the same vector field, so they can intersect. So suppose you have all these integral curves. Pick a point in the manifold. You can look at the k integral curves, one for each x sub I. Those are going to fill out some kind of k-dimensional submanifold at that point, right? If the brackets of your vector fields gave you a new vector field, right, which at that point produces a vector which is linearly independent from the given k vectors you already have, well, that new vector field would come with it a new integral curve, right? And then you'd have a k plus 1 dimensional object, right? So you see that this condition of involutivity is going to be necessary if the leaves of the foliation are k-dimensional, right? We can't have more than, k curves meeting at a point such that they're linearly independent tangent vectors. That would not be possible. If you have a two-dimensional space, you can't have three curves meet at a point, intersect at a point, and have tangent vectors which are linearly independent, right? That's impossible, right? Like in one dimension, you only get one curve. You can't have two linearly independent tangent vectors. Sorry, one dimension is never a very good place to go for examples. Okay, moving on. Now, so what this actually says, here's the definition that Lee actually gives in the book. He says D is involutive if for any two x and y local sections of D, we have the bracket of xy is also a local section. That's what I said, actually. In other words, here's what I didn't say. The sections of D form a sub-Lie algebra of the sections of the tangent bundle. See, this bracket is a Lie algebra. It gives you a Lie algebra structure. It's a multiplication on vector fields. So the derivations form a vector space, and this gives you a way of multiplying two derivations to get a new derivation. But this multiplication is a somewhat exotic one. It's not associative. But its departure from associativity is measured by something called the Jacobi identity. All right. And anyway, you can study Lie algebras independent of this course. They're very interesting. And they have this connection with vector fields as well. It's one of their most important applications, I suppose. Now, I know by now you're missing differential forms. You're like, where are the differential forms in all this? Well, I'm glad you asked. Where are the differential forms in all this? So Rentland says that this stuff is actually not due to Frobenius so much. It was Frobenius stated the forms version of what we're doing. So just to reiterate what we're doing, my main result that I've claimed so far is that the distribution only there exists integral submanifolds for the distribution only if this local defining frame, if the local sections at any point in the manifold are involutive, if they form a Lie subalgebra of the algebra of vector fields. Now, so the other way to look then at this is a question is like, so let's see here. I'm not sure how to introduce this. I need to get rid of this stuff though. I need a place to write. Sorry, I'm trying to find my definition. So I'll give this as the definition basically. If there exist smooth, everything here is smooth by the way, one forms, omega 1. I mean, we've been dealing with smooth operators all morning. Let's see here. Someone wrote a song about that once. Let's see, n minus k, although you guys would know it. So smooth 1 forms omega n minus k such that you don't have that much money. Let's see here. Such that dq is equal to the kernel of omega 1 at q intersected with the kernel of omega 2 at q intersected with the kernel of omega n minus k at q. Then omega 1, omega 2, omega n minus k are local defining 1 forms for the distribution. In other words, we can characterize the distribution in terms of being in the intersection of the kernel for a collection of n minus k 1 forms.
What does the n mean?
What does the what?
The n in between the kernels?
Oh, that's intersection.
Oh.
Yeah, I seem to. It's hard for me to break from my drawing of n. You're right. Sorry about that. So, what would the local defining 1 forms be for our examples so far today? So I could also say that D was basically what? So you might allow me this abusive notation as well. D is generated by omega 1, omega 2, omega n, or it's generated by x1, x2 to the xk. So it takes n minus k. So I mean, it's always this duality of things. Here we have basically hands-on parametric approach. The integral curves of this are filling out the integral manifolds, right? Over here, you're looking at the kernel of these things, right? In other words, basically you set this equal to 0 as it feeds into a tangent. So this has more to do with like n minus k equations, defines a k-dimensional subspace. So in some sense, this is the implicit viewpoint, whereas this is the explicit viewpoint. In our current context, you could think of it this way. So you guys can tell me D is what here? It's dz, right? And it is no accident that, of course, this is what? This is the level curve of the function x, y, z equal to what? Z, right? The differential of the level function gives you the defining differential form. That's not an accident. Here, this one, the description in terms of local vector fields is easy. The description in terms of I would need what? I need omega 1. How many defining 1 forms do you need here? N minus 1 of them. Can you even tell me one of them? How about omega 1 equals to, I don't know, how about x2 dx1 minus x1 dx2? I think that'll do it. See, because if you let this one, omega 1, act on x, what do you get? You get x2 dx1 minus x1 dx2. How does that work? Everything else is 0. And basically this goes with this to give you 1, that goes with that to give you 1, and you get x2, x1 minus x1, x2, aka 0. I think once I write that one down, you know how to get the other n minus 1 of them. You just 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, so forth. On the flip side, what are the local defining forms of this perp? Well, this is easier, right? Oh, I guess to see it, I would need to. You could also look at it. There's some nice things going on here, because whatever is annihilating d perp, it's not going to annihilate x. So like, I think here the omega would be, yeah, x1 dx1. I think so. Something like that. Now, of course, you could, since we're defining things in terms of kernels, of course, you can always take an equation and multiply it by a non-zero scale factor, right? So this description has some sort of ambiguity in terms of multiplication by non-zero elements, okay? But certainly the choice of the omegas, or the x's. I mean, there's a lot of ambiguity in these descriptions. Okay. The looming question then is what? What is the Frobenius? Well, the Frobenius theorem. Oh man, you got me. I think that is the larger looming question. What is the Frobenius theorem? But the more direct question, of course, is what? What does it mean? What does involutivity of vector fields mean for the local defining forms? What's the connection, right? If D is involutive, and D is generated by local defining forms omega 1, omega n minus k, right? Then what does this say about the defining forms, right? Oh, I guess I owe you well, it implies the following. It implies that if, and this is theorem 19.7, part of theorem 19.7 in Lee's book, but if eta is any smooth one form which annihilates D, what does that mean? Say it again. Sends it sends it to 0, right? So that would mean that eta acting on, x, which was a local section of D, is equal to 0 for any local section x of D. Or you could state it in terms of points, which would just be fine. In other words, eta sub p of xp is equal to 0 for xp in dp, right? For all p in u. That's probably better. So in other words, it kills